Okay, hi everyone. Welcome to the Industrial Problem Seminar. It's a great pleasure to introduce Dr. Cora Brown. She got her PhD in our math department in 2020. Her PhD advisor was Professor Carmen Calderer. Since then, she worked at C.H. Robinson, and now she's working at Bridge, where she is a software engineer. And she's going to talk about data science to software engineering and back again.
Thanks, Gilad. Yes, hi, I'm Cora, and I'm going to talk to you a little bit about my career post-grad school, both in data science and software engineering, and kind of my experiences with how they're related to each other. So I'm going to cover a little bit of background, just about me. Then I'll talk about kind of what I did to prepare for a job in industry while I was in grad school. I'll move on to kind of my thoughts about data science products and how they relate to software, and then cover some of the data-driven products I've been working on at my current job, and then finish up with some final thoughts. Okay, so quick background about me. I'm from Minnesota. I was born, raised, and educated here. I was actually born at the U of M. So I have never really left this area. I love it a lot. I went to Carleton College in Northfield, Minnesota for undergrad, and then did my master's and PhD here at the U with Carme, like Gilad said. Post-grad school, I've had two jobs. One at C.H. Robinson as a data scientist, and one at Bridge Financial Technology, or Bridge FT. So I worked at C.H. Robinson for about 2 years. It's a large third-party logistics company. They have a huge data science group, lots of cool problems that they're working on. I really loved my team, but I kind of had a hard time finding my space within the larger organization because it's got something like 15,000 employees. And it was a little hard for me to kind of figure out how data science worked with kind of everyone else. And so I got an opportunity to work for a smaller company, and I took it. I wanted to work with a smaller team, maybe a little more agile, and I've really loved it so far. So we're mostly working on kind of data products just through a software lens. But they have growing analytics needs. So that's kind of the direction we're moving, is kind of more analytical solutions for financial technology. Okay, so while I was in grad school, I did quite a bit to prepare for a job in industry. Some of the overarching things I did, I had a little bit of Python from undergrad, but then I sort of honed in on I wanted to learn how to do data science and prepare for a data science role. So I did a course in machine learning techniques through Udacity, but many of these exist, Coursera, lots of places that you can find these. Then I read what I consider the best introductory text to statistical learning. It's called Introduction to Statistical Learning. And I love this book. It's the authors actually have a similar book that's with a little bit deeper math background. But this book is kind of more of an introduction and kind of more of a overarching kind of how do you think about problems in a statistical way. And I really like it. And then if you do want that deeper math-based information, I love the Andrew Ng data science, or I guess machine learning course that he does. So those are kind of some of the big things that I did in grad school. And then I also did 2 internships, one at Los Alamos National Lab it was kind of a numerical analysis internship, verifying numerical solutions to the heat equation in one of their big heat solving softwares. And then I did a second internship at NextEra Analytics, which is a subsidiary of NextEra Energy, where I worked in time series modeling of wind speeds. So those were both great experiences and kind of gave me an idea of what it would be like to work in industry. So while I was doing all of this, I kind of learned a lot of the Python-based statistical packages. But what I didn't learn was kind of a lot of the underlying stuff that you also need to know to be a data scientist or really to work in any industry position. So a lot of the sort of statistical stuff that I learned, things like SciPy, NumPy, Pandas, scikit-learn, stats models, those are more modeling-based packages. And all of that I did in Jupyter notebooks. And then I used Matplotlib for visualization. So kind of those came up as I was working through the courses and as I was kind of working on some projects. But the stuff that didn't come up is on the right. So stuff like learning Git, which is a version, a cloud-based like versioning system. Things like Docker, which is basically a way to spin up virtual machines. Working in IDEs like PyCharm. So this is not Jupyter notebooks, it's kind of a step away. I sort of learned how to write SQL queries, but didn't really know anything about adding columns, creating databases, and then things like Conda for package management, and AWS is a big one. I didn't know a lot about AWS at the time, and cloud architecture is huge. You will come across it in an industry position. And there's a lot up here. Definitely don't panic if you know any of these or none of these. These are just some things that I came across in learning about being a data scientist and things I didn't come across that I ended up using. So being aware of them is, I think, the important thing. So the other thing that I did in prepping for industry was lots and lots of projects. Some of them I did through the courses, some of them I did kind of on my own. I found some on Kaggle and things like that. But two of my best projects or my favorite projects were through the mini MUDAC competition that Mini Analytics puts on every year. So this is for grad students who are interested in data science. So I did the project in 2018 and 2019 in a team of 4 both times. And I particularly loved the 2019 project predicting soybeans futures prices for like a following week. And we had a team of me, Somi, Sarah, and you. I don't know if you would recognize any of those names, but they were kind of here with me at the time. So for that project, this was our workflow. And it's pretty messy on purpose. So we kind of each took a chunk of data that we were supposed to collect daily. We sent all of that data to 2 of us who then prepared the data and did feature engineering. We then sent that data back out to 3 of us who did different types of models. And then we sent all that data back to 2 of us who did the model post-processing and averaging. And all of this took place in Jupyter notebooks, CSV files, and Google Drive. So it was kind of a mess. I had an amazing time doing this project. I wouldn't have changed anything. And it doesn't make sense to set up a robust software program for a competition. But what it did kind of teach us was that in order to have a sustainable data science product, you do need a process in place. And that process is called software. So how do you get data? How does the data go to your model and how does it come out of it? It's very important. And in order to have a data science product in industry, you need to have something better than 4 people scrambling in Jupyter notebooks. So next I'm going to talk about kind of my thoughts about what data science products look like in that way. So one of my colleagues at C.H. Robinson kind of gave me this idea. She said that data science products are composed of 3 things: data, software, and a model. And so obviously the data is the underlying data for the project. The model is the statistical components that give you the answer you're looking for. And the software is how you connect all of those things, how you combine them, and how you get the product out to the final customer. So if we go a little bit deeper, I've kind of put out some of basically how this process would break out. So you need to fetch the data somehow, you need to organize and store the data, you need to get the data from your storage to your model. Once you have the data in the model, maybe you need to do some pre-processing. You have to run your model, you might have to post-process, then you have to put the output of the model somewhere, and finally have a product that faces your customers. And before I started work, I was really only experienced in these three things. These are the things that you kind of learn about when you are trying to learn how to be a data scientist. You learn how to process data, feature engineering, you learn about modeling, and then maybe you learn about model averaging and using the data at the end. But the other things are also really important. And so I'm going to kind of talk about how those work. So the data fetching, this is how do you get your data in the first place? So for our soybeans project, this meant going to websites that had data and downloading it on our own. Sometimes we did kind of figure out how to scrape websites, but we still had to run that process ourselves. And then the worst case of this was manual data entry, where someone would read the number and someone else would punch it into an Excel spreadsheet or something. So perfectly fine for learning and for a project, but that's not sustainable in industry. You need more of a process in place. So maybe you set up a job to run daily that collects data, or maybe someone else on your team is in charge of putting the data in a database, and then you get to kind of take the data from them. The model input and model output pipeline. So these, again, my experience was running Jupyter notebooks for everything. So you have your data somewhere. You use Jupyter notebooks all the time. And I love Jupyter notebooks. They're great for visualization and data checking, but they don't work very well in terms of actual production level products. And so, things that might be included in these two pieces are packages that get the data from the database to your model and then back out. Maybe you have a database where you store your model outputs, and then also how do external sources access the model output to get to your final customer. And then the last thing I didn't really work on before starting my job was the actual product itself. So I had worked on all of these projects where you get model outputs, and then that's kind of the end, right? You can say my model did this well, you can kind of validate it against reality. But in industry, your model output is going to be used for something. Maybe it's a website application, maybe the model output is making decisions for your company, deciding whether or not to buy and sell stocks, whatever it is. The product is important and is something that data scientists need to be aware of. And then just lastly, you don't need to know all of these things, obviously. Different jobs will cover kind of different swatches of this flow. A lot of times someone will be in charge of data fetching and data organization and storage. That might be more of a data engineering role. A data scientist might be focused entirely on the model. That's possible. And then you might have someone more who works on front end who's actually creating the product. But as a data scientist, you still have to be aware of all of these aspects. And you want to know what's going on at each stage. You want to know where you got the data, how it's being stored. You want to know how you're getting it into your model. And then you need to know what happens afterwards too, because that's the real value of being a data scientist. So here's just two quick examples of models that I ran across in my job at C.H. Robinson. So one example is a model on a schedule. And so this was a model where our data was loaded for us. Daily, we would run the model on a schedule, and we kind of set up ahead of time which accounts or partitions of the data we needed to run the model for. And then the output was stored in a database for use downstream. So in this example, my work really was in the like data pre-processing to model post-processing level. But in the other example, data would come in real time on the fly. The model would have to run, output the model output, and then be sent directly back to the customer. And so this project involved a lot more of these steps because the model had to be in charge of all the things from data fetching to the product. So just two kind of examples of different ways that this sort of pipeline applies in production. Okay, so now I'm going to talk a little bit more about what I'm working on now. So my current job is at a company called Bridge FT. And so they take data from multiple financial custodians. So think Schwab, Fidelity, Pershing. They normalize and aggregate all that data. So the data files from these different custodians look different, but they represent the same information. And so we take it all, we kind of determine what pieces of information are relevant and get it into a cleaned data product. The clean data itself is one of our products. So we serve that back up to other financial institutions who want to use clean data. And then we also provide things like billing for financial advisors and reporting. So how are your portfolios doing on top of that clean data? And then up next, we're going to provide more analytical data products to these customers. So things like, how are your portfolios doing compared to other people's? More of a wide swath of analytics across financial advisors, across custodians, that kind of thing. And so even though I'm not currently working as a data scientist, I do follow this pipeline almost exactly. I'm still concerned with all of these same problems because I am working in a data software company. It's just that the model might not be analytical, it might not be statistical, but something does have to happen. The meat of the process happens in the model, and that's often very mathy. So I'm going to talk a little bit about a project that kind of followed that pattern. So, okay, so switching gears to talking about stocks. When a stock is purchased, it becomes a lot. And so a lot has three things: a date of purchase, the quantity that was purchased, and the original cost. And the cost is really important because it helps you compute, it helps you with tax things, and also for computing gains. So like, how well did your portfolio do over time? And so in this picture, we have three lots. You can see they were purchased at different times. Quantity is on the y-axis, so they've got different quantities. And hopefully we'll be able to figure out the cost of each of those lots. So that's kind of the goal of this project. And if we look at what your portfolio looks like over time, it looks more like this. So this is the quantity if you sum up all of those lots. So if you have 3 lots of apple, the quantity of apple that you have looks more like this, because you had 1 lot and then you bought more. You sold that first lot and then you sold the second lot. So there are 2 ways to acquire a stock. You can either buy it in your account, or you can have it transferred into your account. So when you buy it, this is like going on Robinhood and saying, I want to buy 10 shares of Apple. When you transfer it in, it's maybe you had an account on another site like E-Trade or something. You had 10 shares of Apple on E-Trade and you transfer them to your Robinhood account, or someone generous gives you 10 stocks of Apple or whatever. So these are the 2 ways of acquiring, and the buy creates a lot. So if you buy 10 shares of Apple, that's a lot of 10 shares. Transfer could be multiple lots. You kind of don't know the origination of those shares if they were transferred in. So if we look at maybe an example of 10 shares of Apple that someone gave you today, perhaps they were all purchased together 9 days ago for a quantity, or maybe they were purchased at different times for different quantities, and for different amounts. So when doing this project, we have information from those transactions. We have the transfer information, and we also have the buy information. So for the buys, we have the date of purchase, the quantity, and the cost. We kind of have all the information we need. But for transfers, we only have the quantity. And then the other piece of information that we have is something called cost basis records. So these come in daily, and they are they provide date of purchase, quantity, and cost for each lot that they represent. So this is actually the lot information, and our goal is to match cost basis information to each transfer. So the way that this works is kind of a daily process. So on the first day, there was no information about the transfer because it hadn't happened yet. Second day, same story. On the third day, we have information from the transfer, and we have new cost basis information as well. And so we can make a match to the buy on quantity and cost. And then we can also make a match to the transfer on quantity. If there's another transfer that happened later, we can do the same process, but we have to start further back. And then we can kind of step through the days. We get a new buy information here. And then finally, we can match that second transfer after several steps. So one of the most interesting aspects of this problem is what happens when a transfer represents multiple lots. So in this case, you can see we have two lots that kind of sum to that total transfer amount. And this is something called a subset sum problem, which is, does any subset of my set sum to my desired amount? And this is an NP problem. There is a pseudo polynomial solution that uses dynamic programming. But many of these cases still ended up being kind of too intractable to handle. So part of this project was figuring out how many subsets can we try to match feasibly? What size of the sets can we look at? Often we'd have 200 lots to match to 5 transfers, and that problem becomes, well, that's 3 to the 20 different subsets or something. And so even with fast programming, it's not feasible to check all of them. But we can check some of them, and in this case, we would get that transfer matched to these 2 lots. And then another tricky thing to consider is that you can also get rid of stocks, right? You can transfer them in, but you can also transfer them out. You can buy them, but you can also sell them. And so what ended up happening with a lot of our examples was we'd have cost basis information that matched 2 transfers, or a buy and a transfer, or nothing matched anything. That happened quite frequently. And so there are a lot of cases like this that became kind of unsolvable, but we also were able to get a lot of cases solved. So the kind of model shape that we ended up going with is basically a deterministic decision tree. And so basically you are stepping through the days. For each day, you have kind of a hard-coded decision tree. Can we make these matches or not? And so rather than training a decision tree on our own, we actually built one in, which is pretty common in code. You want business logic kind of baked into your product. And in this case, that's kind of the only thing that's going on. But it's still pretty complicated, and it was a really interesting and fun project to solve. So if we just go back to that kind of data science software pipeline again. This is how this project fits into the wider scope. So the data is fetched by daily drops from those custodian sources like Schwab. The data is stored in a database. Weekly, we run this model. So we had to set up a job that will run the model once a week. For data pre-processing, we need to make sure that we're looking only at data that matches the same account, stock, and date. And then we actually run our decision tree. We validate the results, store the output in the database, and then the actual product is the fact that these matches are available to the customer, and they can now do tax calculations using the cost basis information. So I only included kind of very limited ones here. Basically, as you go through matching, there's decisions on like whether or not to accept a match, basically. So like if you had 2 transfers for the same amount, or a transfer for $10 and a transfer for $8 and a sell for $2, so you end up with 2 lots of eight shares, or I don't know why I said dollars. So yeah, basically you have to make sure that you're not matching anything that you shouldn't match, and you're only matching things that should match. Yeah. So kind of in conclusion, I just want to talk a little bit about comparing my 2 jobs. As a data scientist, I kind of worked on these areas, not so much the model output and not so much the final product. And then as a software engineer, I worked kind of on these areas. And so still a lot of the same areas, not so much statistical modeling, but still, pretty in-depth mathematical thinking going into how do we solve these problems. But I did have to kind of care about the whole pipeline, regardless of whether or not I was working on it. And as both, I get to do some of my 3 favorite things, which are data visualization, exploration, and validation. And I still do all of these in Jupyter notebooks. I do love them. I just kind of recognize that they're not perfect for, production level work. So in conclusion, as a data scientist or in any job, you will probably do a lot more than just modeling. But designing and these production processes can be really fun and challenging too. There are a lot of things to think about, from efficiency to stability. You kind of have to think about all of those things to create a final product that's production ready. So I would recommend figuring out which of those pieces you like to do. Maybe you like database building and management. So you could look for jobs more like a data engineer. Or maybe you really do prefer the modeling part and you want a very statistical job, and those exist too. And then my final point is you definitely don't have to know everything. Your company will train you. Even if you try to learn AWS really well, they'll have specific things they do that you will have to learn. And no one expects you to know everything when you start a job. I certainly did not. I still do not. But being more aware of kind of what all goes into creating a good product, I think is something that's valuable. So, questions?
Slides for Oh yeah. So the data visualization. So in this project, will be part of visualizing things, right? There's some kind of things. So what kind of visualization do you have?
Like for this one, or
for this, and whatever you're working with, part.
Yeah. So I used a lot of pictures like this. Actually, I usually included like a line So I would usually have something like this. And these really help me see like which pieces of information were supposed to match the transfers or the buys or whatever. At C.H. Robinson, I was dealing a lot with like truck costs versus time. And so I also would just plot a bunch of truck costs. I use a lot of like kernel density curves to figure out like distributions of things. I've been doing that kind of frequently to check maybe if the data is valid or something. You use a lot of things like that. But mainly I've looked at, hundreds of these.
So you have to, all these content, or you have a way to visualize together something?
Yeah, for these, I was definitely looking at individual cases. I would kind of run maybe a program to see which ones I should look at. But for these in particular, like in debugging, I like to look at a lot of individual examples for sure. I did do some dimension reduction. So this was more of like this is kind of straightforward, basically 3 dimensions, I guess. At C.H. Robinson, I did a little dimension reduction, but mainly for the features I've worked with, plotting them individually has been pretty valuable. Yeah, maybe like a cross, like the distribution, the bivariate distributions of the variables on like a plot like this. I've used those pretty frequently.
And do you use these visualization also for data exploration?
Yep. Yeah, a lot. Yeah, my current company doesn't actually use Python, but one of the first things I had to do was get Python and Matplotlib up and running so I could actually look at the data. Yeah, for me, that's kind of the very first step and the most important part.
Exploration is something you learn with all, right?
Yeah. Definitely doing the soybeans project. For this, we had to create plots and stuff as part of our presentation. So I learned a lot of, how do you present information in a good way. Part of the questions of these, part of the goal was making the predictions, but part of the goal was also like figuring out which features are important. And so for that, plots are really helpful. You can do things that like plot feature importance and stuff.
And by the way, this presentation 100% was presenting the material itself. So how kind of your work out presentation?
At C.H. Robinson, it was pretty frequent. At my new job, I've just done one on this project, but I'm still kind of ramping up. But even presenting to other data scientists or other engineers, it's pretty important, yeah.
So, how those because that's very
Right. How do you make good presentations? I guess you always kind of want to have a goal in mind in your presentation and work towards that. And explaining things like a lot more than maybe you think that you should. That's something that definitely for these 2 projects, the audience is business people who maybe know the domain but don't know the analytical background at all. But even then, you want to explain the problem, you want to explain kind of the terminology that you're using in the problem. And then you want to talk about the technical side, but maybe not go too in depth into what you actually did. Obviously, it depends on your audience, though.
So some of those people in the groups are.
The judges for these were yeah.
Right, but you can go on to it.
Oh, yeah. A lot of presentations are for kind of the stakeholders of the project who aren't technical, but the people deciding to have done the project in the first place. Yeah, so lots of presentations to people who know the domain, but not the math, I guess.
Probably the best way person produces the
Yeah, these were invaluable to me. These competitions were, yeah. I mean, they were very challenging, but some of my favorite times in grad school also. So, yeah.
reason.
Oh yeah. Yeah, this is an advertisement for them. I can't recommend it enough, even though, you know, we were at this stage quite a bit, but in a good way. So, yeah.
Sure.
Let's see. So in your final slide, you showed the data, that sample, right?
Oh yeah.
Data software model.
Oh yeah.
And also through the cycle of this problem, at some point there's a model.
Mhm.
How much of say, information you can put from anything? For example, when you mentioned the problem of the track,
Mhm.
and you did before, I don't know what the problem was, but suppose imagine that you would try to design the schedule of a truck company that says that's distribution around the Twin Cities, right? So of course, you have lots of data about times and many things, of course. So, but now suppose the transportation department, so the Minnesota transportation department, actually the Twin Cities, and so also has very sophisticated models of traffic. Some of these models are TV models.
Yep.
So how could you bring, say, your, the spot model, how many foreign or external models can you actually fit there? So you could have this huge sets of data, right?
Yep.
How could you fit, say, something that's TV based? Does
Yeah.
it make sense? Does it ever happen? Is it useful?
Right. So I can't speak to whether or not it happens. I haven't used it. But I would imagine if a PDA model outputs something like a heat map of where traffic would be or something, you know, you could sample points from it and kind of condense that information into like a discrete, you know, if you get some kind of discrete information, even if it's a lot of discrete information, that should be pretty easy to, or not easy, that should be pretty doable to fit into a model. And like, that would maybe be part of like the input pipeline. You would have to collect data from external sources like that you're not storing in your database, but that you're inputting into your model. Yeah, definitely doable. Yeah.
Then another thing that is independent, and maybe we can talk about it some of the time, but I'm very interested in the thing that you give in Los Alamos, right?
Oh yeah.
About how they actually calculate heat equations in industry.
Yeah.
But
Yeah.
in our course, we are doing we're working on a problem. Basically, it involves the heat
That.
equation in the industry. And I want to see how it's really done in in really serious setting, right?
Yeah, yeah.
The kind of we're approaching it like a direct and things like that.
Yep.
But so I just want to see
What
they do.
they were doing, yeah.
So this would be very good. Maybe at some point we can talk to these people.
Yeah.
Say, pushes the project, but some people ChatGPT, they use better. Yeah,
Hmm.
we'll see. So
If anyone at home has a questions, you can type them on questions and answer box.
last question. Yeah. So we can have the follow-up
Mhm.
discussion with the student. Okay, by way.
Okay, let's thanks the speaker again. Thank you, Catherine. Yeah, we can stop share. I think we can end it.